Hello and welcome back. In this video we'll start section 7.3, which is on estimating the variance and standard deviations of populations. In the previous couple of sections we looked at estimating proportions and means of populations. And these were quite nice because when we sample proportions and when we sample means, the samples will be normally distributed, as in the sample proportion, the sample means will be normally distributed. So this normality lets us estimate the actual value of the mean and of the proportions very easily. When it comes to estimating variance and standard deviations, we run into a little bit of an issue. So first of all, with variance, when you calculate a sample and you find the variance of the sample, you can use it to estimate the variance of the population. This is because the sample variance is a unbiased estimator for the population variance. The standard deviation, on the other hand, it's not so nice. The sample standard deviation is a biased estimator. However, it's often close enough that it's used as a point estimate for the population standard deviation. So essentially, we can use our sample statistics to estimate our population parameters in this case. Even though it's not the best one, we will quite often use the sample standard deviation to estimate the population standard deviation. The biggest problem comes in constructing confidence intervals. So when we take samples and we look at their variance and their standard deviations, these are not going to be normally distributed. So we have to use a different distribution to come up with confidence intervals. And the distribution of variances and standard deviations is called the chi-squared distribution. So this letter here kind of looks like an X. This is the Greek letter chi. So it's a chi-squared distribution. And this is what it looks like. You can see that sort of at 0, it will start to rise up, and then it'll continue on for all positive numbers. So why can the chi-squared distribution never be negative? Well, when we're talking about variance and standard deviation, you can't have a negative variance and you can't have a negative standard deviation. This is because these numbers refer to how spread apart the data is, or the data are, excuse me. And if things can't be spread apart in a negative fashion, it's either not very spread apart, in which case it'll be closer to 0, or the data is going to be are very spread apart, and it will have a large standard deviation. So the distribution of standard deviations and variances is going to be entirely positive, and because of this, our distribution is going to be skewed to the right. So it's not symmetric because it sort of bunches up at 0. And it's going to be skewed to the right. We have a long tail that comes to the right. So we'll have to treat this a little bit more carefully. But in essence, the critical values that we'll find are essentially going to be the same thing. If we want to find a confidence level, that's going to be 1 minus alpha. We're still going to find the area essentially right in the middle, and this area in the middle is going to match the 1 minus alpha. So the area here in the middle is going to add up to 1 minus alpha. The extra alpha part is going to be off to the sides. So over here, this will be alpha divided by 2. So this is how much area there is on this side of the curve. And then over here, this will also be alpha over 2. So we want to put the same area on both sides, but because it's not symmetric, how do we decide where it is? We just have to use some sort of calculator or table to come up with these values. Since it's not symmetric, we could essentially put these anywhere that we wanted to. So we just have to be a little bit careful. So one thing to notice is that this is the description of the distribution. So chi-squared is going to be n-1 times the variance divided by the variance, as in n-1 times the variance of the sample, n-1 times the variance of the sample divided by the variance of the population. N here is just going to be the sample size. Sigma is the population standard deviation, so sigma squared is the population variance. This is a fixed number, so this is fixed. That doesn't change. And also, once we take a sample, this doesn't change. Once we pick a sample size, this doesn't change. The sample that we pick could change S. So S is the only thing that's a variable in here. So chi-squared is going to depend on S squared. One other thing to notice here is that this distribution depends on which value of n we choose. If we pick a larger sample size, n changes. If we pick a smaller sample size, n changes. N-1 is called the degrees of freedom, just like with the other ones. And when we pick a different, let me do this I'll just do it in the same color. When we pick a different degree of freedom, we'll get a different graph. So this is a smaller, this is the graph for a smaller degree of freedom. And this is going to be the graph for a bigger degree of freedom. So the bigger the degree of freedom, the flatter the curve is going to be, and the more spread out it's going to be. The area under both these curves, because this is a probability distribution, the area under the curves is going to be 1. It's just a little bit flatter and more spread out. So let's go through and calculate a couple things. So I've introduced this question, but I'll need to tell you a couple terms. So chi L squared and chi R squared. So when we are looking at the chi-squared distribution, which looks something like this, and we're told that we have our 95% confidence interval that we're trying to construct. We want to find 95% of the area to be in here, and we have the rest of the 5% of the area should be beyond these 2 points. So over here, we should have half of that remaining 5%, which is going to be 0.025. And then over here, we should have the other half. So again, this is going to be 0.025 here as well. So these numbers, so this number here, this is going to be chi L squared, as in the left critical value for chi-squared. And this is going to be the right critical value for R squared. And furthermore, this curve right here depends on the size of our sample. So the degrees of freedom for this graph is going to be 21, which is 22 minus 1. So the question is, how do we construct these? Well, there's a couple of ways to do this. I am first going to use STAT216, and let me zoom in once here. So in STAT216, we can go to Stat, we can go to Calculators, and then right here we have the chi-squared calculator. And when we open this up, it pulls up a little image of our chi-squared distribution. We can then adjust the degrees of freedom and the areas that we want to compute. So for instance, in this case, our degrees of freedom was 21 because the sample size was 22. And we want, for instance here, to find the area to the left of this value to be 0.025. So coming back to STAT216, we want the area to the left to be 0.025. And when we compute this, we get this value. So 10.28. So after using StatCrunch, we found that this is going to be equal to 10.28. Over here, let's flip the area over, so we're looking at the area to the right, and we'll find the right critical value. So the area, again, let's see here, let's flip this over, and then we want the area to be 0.025. And then we compute this, and we see that the right critical value is going to be 35 point, let's say, 48. Great. And we found our two values. There is a second way of doing this, and this is to simply look these things up on a chart. So let's go to, so I pulled up this question, and here we could go to question help and go to StatCrunch to open up StatCrunch to do this in the same way that I just did. Or we could look at the table of all these icons. And the table is a little bit hard to read since it's it looks pretty poor quality. But what we'll see is that the degrees of freedom is listed on the left and the right. So we can come down to 21, and we can follow this across to figure out our critical values. And the question is, which column do we want to belong to? So this is referring to the area to the right of the critical value. So on the right-hand side, we wanted the area to the right of the critical value to be 0.025. So we want this, which is the third column from the right. So if we come down to 21, we see that we have 35.479, which matches 35.48. I just rounded to one less significant figure. So that matches. Now, our chart only talks about area to the right of the critical value. So if I come back to this picture, what I should do is look at the area to the right of this critical value, which will include all of the area in the middle, so this 0.95, and this area over here. So total, we've got the 0.95 in the middle, plus this 0.025 coming off the right-hand side to give 0.975. So again, the area to the right of the leftmost value should be 0.975. So when we come to our graph, yep, we have 0.975, which is the third column. And if I scroll down to 21 degrees of freedom, we see 10.283, which matches our 10.28, just rounded to one more significant figure. So, two ways to calculate critical chi-squared values, either via StatCrunch, via the chi-squared calculator, or looking it up in a table.